But for now, we'll just stay with design for a while. So this is on the new edition. It's chapter 14, 14.1 and 14.2. And on the old edition, it's chapter 15. So, so I'm going to do design, again, using the company database as the motivating example. So one of the things I asked in the last class was, why this design? So you can see the design on the left side. So the question is, why this design? I mean, you know that this is not the only design possible. There are many, many designs possible. And by design, I mean, the tables, the attributes in the tables, why you have what are the primary keys, why were they selected, the foreign keys. So, so the question is, you can have many designs. So why this design? Is this the best design, and why, if it is the best, then why is this the best? Are there many good designs? So it is, uh, so what we're going to do in this cover in this class is, how do you come up with a good design? What is a good design? And what is a bad design? So we're going to be talking about database design theory. So there are a few. So first I'll do the informal, um, the informal design techniques, and then I'll go on to the formal design techniques. So the informal design techniques is some goodness test. So it's a goodness test. So from the informal design is, when you look at it, is it easy to understand the design? So if you look at the company database, it is relatively easy to understand. You have the employee table, about the employees, then you have a department, the project. So those are kind of obvious that they're kind of independent, what I call entities, so or independent tables. So it makes sense to have those three tables. Some of the other questions may not be as obvious. So for example, the dependent, why not just put it with the employee? Why do we have a different dependent? And the same thing what works on, why not just connect it with the employee table? So there are, so there are some things that may not be that obvious, but the whole idea is that even if the way it's been divided, is it easy to understand? So among the goodness test, we talk about things like ease of understanding. Another very important issue you have to deal with. I mean, the whole idea of having a database is to issue queries. So is it easy to issue queries on the database? So, I mean, till now, you may not really think about it, but the database structure, I mean, all our queries are very dependent on the layout, on the structure, or the design of the database. So if you have, standard queries that you do, for example, on your on the My Courses, I mean, very common queries would be list all the students in this particular class, or for a particular student, list all the courses they're taking. So, I mean, are those queries easy to formulate, or are they really difficult to formulate? So that's another thing you have to look at. Is it easy to formulate queries? Um, then another thing which may not have been that obvious, because nowadays you're doing stuff and you haven't really given it any thought, But remember that many of your queries are, they join tables together. They're joining multiple tables together. Um, so when you join multiple tables together, is it possible that the joint table um, ends up having wrong information? So right now what I'm saying is not going to make that much sense, so I won't write it out. But that's another thing you'll think about, is that when you join tables together, is it possible that the joined tables are not, don't contain all the right information? So yeah, so that's another thing that one has to think about. So um, um, and again, I just wanted to, I think I got all these designs out here. So let me, okay, it's not this one. Okay, so anyway, I'll get to that anyway. So the next thing, so this is all um, from the user end, but on the administrative end also, you want to look at the physical aspects of the data being stored, because ultimately all the data is on the disk. So databases are large to begin with. So you really want to reduce the footprint of the database, that is, reduce the amount of storage they're going to use. So storage requirement should be as minimal as possible. So for example, in a database, if you have a lot of redundancy and you're storing the same information many times, you could, you're increasing the amount of storage. And then another thing from the physical side, is it easy to retrieve and easy to update? So Um, so that is, so again, when you look on the left-hand side, we have, in the original schema, we have employee and we have department. So instead of employee and department, so when I say, suppose my table was, um, so, so instead of employee department, suppose I have a new table called employee department, and I'm combining the information in the employee table and the department table. So let's say in this new table, I have the following fields. I have employee name, social security number, birth date, address, D number, D name, and department manager's social security number. Okay, so I'm combining the employee table and the department table together. So now when you look at the on the left, when we look at the this employee department table, so this is the employee department table. So this table, if you look at it, it has a lot of, it has more redundancy than your previous table. So for example, each time you're writing department number 5, you have to write the department name and the department manager's social security number. So right there, there's a lot of redundancy. Um, so so when you look at this table, if your original design had been like this, then it's, by just looking at the table, and even without having a logical understanding. So, for us human beings, when we look at the table, that employee is one entity and department, they're two separate entities. They're kind of independent. They don't really depend on each other. So for us, it makes sense to divide the two into separate tables. But even if you had no knowledge, no logical understanding, and you were just blindly looking at the data, you can know by looking at this one table, employee department, versus looking at these two tables out here, employee and department, that this is not a good design, because you can see a lot of redundancy when you just look in, even without any logical understanding. So that is, a bad design. So So the problem, so let me just write the problems with employee department. Okay, and again, this is the informal design, okay, consideration. So when I look at this table, you know, um, so the question here is, suppose I create a new department, say department number 3. So when you create a new department, suppose, I mean, I've just created it and there are no employees in the department. How will I add this department, a new department into this table? So, so this would be called, you know, problems with insert. So, okay. And similarly, just on the other side is delete. Suppose I delete the employee James Borg. He's the only employee in Department 1, the very last row of the table. If I delete him, do I lose all the information about department number 1? So that's another problem. Is just like you have insert, you have the same problem with delete. So you delete the last employee of a department. That would imply that you have, you lose the department. So that's again not something you want. And then finally, update anomalies or update problems is, one of the problems with redundancy is that what happens if, because after all, someone's typing in this information, I misspelled the name research. So instead of spelling, I write it as RESERCH. So now it looks like department number 5 is research with the A, the correct spelling, and another research. So that's the problem with redundancy, is that you can make data entry mistakes. So like I mentioned, so research. So you have, or let's say that you change the manager's social security number. I mean, so different managers for the same department. So all of this, if you have a table like this, you can have all these 3 issues, insert, delete, and update issues. So a very informal design consideration is, do not put 2 independent tables, do not combine them as one table. So that's rule number 1 is, do not combine 2 independent entities into one entity. Okay, so one entity or one table. So that's one. So that's, and one, the first informal design consideration. Now, another informal design consideration is that, if, let me, do I have it here? No. Suppose I decide to combine, okay, so out here, suppose I decide to combine the employee table and the dependent table. I say, you know what, I don't want to have two different tables. I combine these two tables. So when you combine these two tables, of course, the redundancy thing will come up. But the problem is that many employees do not have dependents. Not everyone has dependents. So when you have several dependents, so for example, if I have several dependents, then there's a lot of redundancy for my data because all my data is repeated each time. But the problem is if there are no dependents, then your row, there are a lot of null values. The entire dependent table would have null values. So whenever you come up with a design, you always try to minimize. One is redundancy, but you also try to minimize null values. So that's the next rule is minimize and null values in tables. So what I would say is that do not combine M and dependent, because dependent, you will end up with a lot of null values. And then this last one, and I know this last one has to be, I'll have to kind of show you an example to explain this. But the idea is that your design should not generate false data. So I want to give you an example of how you could generate false data. So let's take this a table called employee project. So remember that right now we have a project table and an employee table. So instead of this, I'm going to create a table called employee project. And so this table has, so we have a table R, and this table has social security number, P number, OS, E name, P name, and P location. Okay, so I have, suppose my original design, I have this employee project table, and I look at this table. So this is table R, has 1, 2, 3, 4, 6 attributes. And when I look at the table, I say, you know what, there's just too much redundancy in this table. So I'm going to split it up. So okay, so I'm going to say, you know what, I don't like this table. I'm going to have two tables, R1 and R2. So instead I'm going to have R1 and R2. And so R1 is table 1, which has, I'll call it employee location. And this table has the following attributes. It has E name and P location. Okay, so I have the table employee locations, and then I have table R2, which has employee, let's call it project locations. And this one has social security number, P number, OS, and it has social security number, P number, ours, and it has P name. And I put in P location also out here. So, so now I have decided that I have these two tables. I just randomly decide I'm going to divide. I know it doesn't really make sense, but I'm saying, so what? I have so much redundancy in this other table. I'm going to have these two tables, employee locations and employee project locations. And these are the fields in the two. And so the connecting what connects, remember that every table that you have should have some kind of thing that connects together. So what's connecting these two tables is project location. Okay, so I'll just, okay. So so the question is, so that's what I'm going to show. So I've created, let's see. Yeah, so this is the table employee project on the left. So this is the original employee project table, and it has a whole bunch of redundancy, like I said. So I decided to split it up into two tables. So these are the two tables, employee locations and employee project. By the way, I do put up PowerPoints. I put up all the PowerPoint slides for SQL, and I'll put up the PowerPoint slides for design. So everything that I'm showing on the left, I'll put it up on my courses. So this is the these two tables. So you have employee location, and then you have employee project. So I have these two tables out here. So the question is that when you join R1 and R2, so let's say I join these two tables, I do R1, join R2, and the joining uh, column is project location, because that's the common thing. So when I join it, I find that R1 and R2 will not be equal to the original table R. So this is the join on the left. This is the table that joined, that is the join of, um, I mean, it's a part of the table. The table is much longer. It's one part of the table. But when you look at this table that is join of these two tables is not equal to the original table. This is the original table, employee project. But this original table, uh, is not equal to this table. So that's one of the things, because so far, you know, when you've been doing queries all along, you've never really ever, I mean, most of you wouldn't have given it any thought that when you're joining all these two tables, is it possible that you could get false information at the end of the join? Um, so that's what I'm trying to say, is that splitting tables, you know, is not trivial. When you so on one hand, you know, when you have this this big table with all of these attributes, you say, okay, I have too much redundancy, I have too much null values. I mean, this one big table doesn't make any sense. But when you go from one big table, you decide to split into multiple tables, you have to be careful. You can't just there's a bunch of rules you need to follow when you divide tables. So actually, that's what I'm going to be talking about really initially when I do design, is do you how do you um, you know, how do you come up with the structure of tables? How many tables? What attributes should the table have? Because when you do design, a lot of times initially, you might have one big table with a bunch of data, I mean, attributes in there. And then you are trying to figure out, how do I divide this table? So luckily in database design theory, there are a bunch of rules um, that you can follow to figure out how to divide tables. So does anyone have any questions? I hope that the informal design considerations, because now I'm going to move on to formal design considerations. So I just want to make sure you understood the informal design. Okay, so then I'm just going to go back to the single. I just needed that um, for the informal. So now I'm going to move on to formal design considerations. Okay, so so I'm going to do all the, I mean, the various steps for this one. So so when you start, when you're doing formal design, so let's say for the company, suppose you are a designer for the company database, so one, you first figure out, you don't, come up with all the individual tables right up front. First, you might come up with a large table. So for example, you might decide, okay, for an employee, I need all this is the kind of information I'll need for an employee. I need the employee's name, his address, all his personal information. Then I need to know which department he's working in, what projects this employee is working in, um, how much salary the employee is earning. I also need to know who are all the employee's dependents. Then I might want to know all about his retirement stuff. So there's a lot of information. So initially, you're just talking to the company people, trying to figure out what all information is there connected with an employee. So initially, you don't start with tables, you just get all the attributes, kind of all the information that you need to collect for an employee. So you start with a relation. So you start with one relation. You can think of it as a universal relation. So you put all the attributes, you throw all the attributes into one table. So you start with a relation that has all the attributes. So again, I'll go back to the employee project since we started up with that. So for the employee project, so initially you don't have to split it up. You start with the employee project and then you have all these attributes. So you have social security number, you have project number, then you have e-name. I'm just put a smaller table. So I'm not putting first name, last name, etc. P name and P location. Okay, so that's the first step. So in step 2, I'm going to will talk about what these things are right now. So I'm going to throw in some words right now. So the next thing what you do is you specify the functional dependencies. So you specify the functional dependencies. So they are FDs and the multi-valued dependencies. These are the MVDs. Okay, and that's pretty much, this chapter is about explaining, trying to figure out what do you mean by functional dependencies and multi-value dependencies. Now, so one of the things is that, again, this is all the design phase where you, the systems designer, is going and talking to whichever company you are trying to build a database for. So you're speaking to the people, trying to figure out, so you find out, okay, this is all the attributes that I need to put down. So then you talk to these employees and try to figure out what is the relationship between the attributes, So is it possible, for example, for an employee to work on multiple projects, or can an employee only work in one project? Um, can an employee work in projects that are not belong to his department, or can he only work on projects in his department? So you have to find out, can a project be in multiple locations? Can a project location be different from a department location? Um, so, so when you're doing system design, you have to, when you talk to a client, you also you find all the attributes, but you also have to find out the real relationship between these attributes, a real world relationship. So this has nothing to do with it can change from company to company. So maybe in your company the rule is that yes, an employee can only work for projects in his department, and so it's really based on a company. So this is, so these functional dependencies and MVDs are based on real world relationships. And again, here I would like to also just make a point here, is that sometimes when you talk to an employees, maybe you talk, so let's say I'm the system designer and I'm making the database for UNH, let's say, and I'm talking to people and they say, you know what, yes, you know, a faculty member can only teach classes in their department. They're not allowed to teach classes in other departments, you know. So for example, I work for the CS department, and if I cannot go and teach a double E class at all, but then, so that's what, let's say, you know, whoever I'm talking to tells me that. But then, you know, when there are things that you can learn from the data. It's not always that the people you're talking to know everything. So you could look at the data and then you realize, you know what, that's not true. You know, Liz Warkey, she teaches for the CS department, but I also noticed that she's teaching a class in the math department. So, you know, even though the manager told, I mean, this person I'm talking to told me this, you know, but I've realized that the data is telling me differently. So here, so when I say based on real world relationships, it's not only by talking to the people in the company, but sometimes you have to also look through the data. You have to pass through all the data that's currently there and see, you know, what is the relationship that is there. But whatever relationships you specify, these are things that you have to put down. I mean, all of those have to be somehow encapsulated in the database. Um, so all of this stuff is these functional dependencies and multi-value dependencies. Once the database designer figures this out, then they will, it's, you know, they'll have to somehow incorporate it. So I would say, so all of this is input by the database designer. Mm. Okay. Or is it done by database designer? Okay, so any questions so far? Okay, and all of this, so it's based on real world relationship. It's input by database. I think done by database doesn't seem to make that much sense. Let's see, input. And also it is a property of the data, you know, because that's why I said that even if you know, you can look at the data and see that some of this relationship. So it's the property of the data. Um, and again, I don't know if I mentioned this in the early classes. I know that data in English is plural, but in database, when I say data, it's kind of, you use it in a singular manner, not as a plural. So for example, you know, there's some things that are very trivial. So for example, all of us know that the social security number is, if you know the social security number of a person, then you know the name of the person, you know. So, or in UNH, if you know the UNH ID, then you know the name of the person. So those are things. So I'm going to talk about, so for a while, so right now I'm going to talk about functional dependencies a little bit. I may talk about more later. I won't talk about multi-value dependencies right now. So I'm just going to talk about functional for a while. So, so, so since I said that, you know, the social, so once you're given the social security number of a person, you know the name of the person, right? So the social security number will determine the e-name, the employee name. So that's what you would say. You would say that social security number functionally determines e-name. Or you can also say that e-name is functionally dependent on social security number. So you can say it either ways, it's the same thing. So similarly, when you look at the database design, you also find that the project number determines project name. So if you know the number, then that can only be the name. Also, let's say for the company database, you also find that the P number, let's say, determines P location. And let's say for social security number and P number, so you determines the number of hours that you work. Let's say that that these are the things you learn as a designer when you're talking. You find that P number, SSN determines e-name, which is trivial, but then it is pretty much standard. But then for this company, you find that P number determines P name. P number will also determine P location, and SSN, P number together will determine the number of hours the employee works. So, okay. So let me just write down a small bit, and I just want to ask you if this is correct, the data that I wrote down. So I have social security number, and I have e-name, and I have 3, 4, John, Mary, and then I have, okay. So this is a small table I've written on the left, and I've said the social security number determines e-name. So given that, does this table that I've drawn on the right out here, does this table satisfy, is it violating or satisfying this rule? SSN determines e-name. Because I do have 1, 2, 3, 4 and John and 9, 8. So I have John appearing twice. So my question to you is that given this, is this a valid table?
Yeah, I think it is. Yeah, I think it would be.
Yeah, but you have John twice, right? I mean, with 9, 8,
True.
6. So what? So that's a. So why do you think your answer is correct? By the way, it is. This table is valid. So my question is that, um, um, I do have John twice appearing out there. Is that
I,
violating this SSN goal determines e-name?
so it's not. I mean, if we were doing the e-name, goes to the goes to SSN, then we'd have, then it would be a problem.
Yeah, so that's the thing, it's your that sometimes people don't really understand this, A implies B, what does that mean? So um I mean, let me just put it. So what I'm saying is that if SSN is equal to 1, 2, 3, 4, then e-name is equal to John. That's what I'm saying. I am not saying, so what this means is that, okay, so this is equivalent to saying, what I just wrote is equivalent to saying if e-name is not equal to John, then SSN is not equal to 1, 2, 3, 4. Now, these two are equivalent statements. If SSN is equal to 1, 2, 3, 4, then ename is John. If ename is not equal to John, then SSN is equal to 1, 2, 3, 4. But I am not saying that if ename is John, then SSN is equal to 1, 2, 3, 4. That is not what this is saying. So that's the thing you have to really understand. Okay, so I do want to say, so if I said if ename is John, then SSN is equal to 1, 2, 3, 4. And that is not what SSN goes to ename states. So this is what it states. These two are both equivalent. So, and I am going to spend a little time on functional dependencies because it is very much the crux of understanding database design. In fact, functional dependencies, you really need to know that in order to, I would say, pretty much do any kind of proofs and things like that, theorems and proofs. You have to understand this. And a lot of times people don't totally get it. I mean, students don't get it. So I do spend a little bit of time on it because it looks very trivial. But unfortunately, a lot of times people take it to mean this, and that's not what it means. So what it really means is that if A, then B, A implies B. And so that's equivalent to saying not B, then not A. So that's not B implies not A. Oh. So these two are equivalent statements. So okay, so you can either, they're equal, they're saying exactly the same thing. So I'm going to give another example. So again, see, right now I'm using examples like social security number, ename that you really know, logically a human brain understands it. So even if you don't understand the math part, this part of it, your brain understands that social security number is unique. So even without really understanding this or this, you would be able to answer this correctly. Similarly, this next one too, I just want to show, for example, I say, if today is Sunday, then school is closed. That makes complete sense, right? So if, Sundays we don't have school, so that what I just said is equivalent to saying if school is open, that school is not closed today. So if school is open, then you know that today is not Sunday. Based on that statement I just wrote, I know that if someone told me, you know what, UNH is open today, then you know immediately, okay, then today is not Sunday. But if I said that if school is closed, that does not imply that today is Sunday. School could be closed because it's spring break. It could be closed because it's, Christmas. It could be closed for any reason. So that's the thing, just because school is closed does not imply today is Sunday. So the above statement, the statement in brown, does not mean this. What I meant is that what it means is that a school is open, not closed, and today is Sunday. So these two statements are equivalent statements. So that's the thing about functional dependencies. So I will be coming back. So this is a formal design considerations. Step one was you start with a relation that has all the attributes. Then you specify the functional dependencies and the multi-value dependencies. I will talk about MVDs later. They are a lot harder than functional dependencies. Lot harder. So I will only get to it a little later. I'm not even going to bother to explain it right now. I just want you to know that when you split tables, you have to also factor in more than functional dependencies, also multi-value dependencies. So once you determine all the, so step two is you determine all the FDs and MVDs. And then in step three, 1, 2, 3, yeah. So finally in step three, you divide the table. So you decompose the table. So in our case, the table was employee project table. So you decompose the table with all the attributes into relations or tables that are in normal, sorry, let me write it down here, that are in normal form. So you are dividing the table into tables that are in normal form. And if you divide your tables into normal form tables, then you will never get the anomalies that I showed you earlier, the insert, delete, update, and the join, getting wrong data. You won't get that. So that's the thing is that a set of tables in normal form. So a set of tables in normal form does not suffer from insert, delete, update, and join anomalies. So if so the example I showed you earlier, when I divided employee project into those two tables, R1 and R2, and then I got all those spurious, the wrong tuples, the join anomaly that happened, that would never have happened if I had divided the table employee project into two tables that were in normal form. So, so if you have the original table, so original table, if you have R, and then you have divide into R1, R2, where R1, R2 in normal form, then R, you'll always get the original table R from the join of R1 and R2. You will never get a wrong table. You're guaranteed that the table will be, will be the join table. You'll get back the original table from the join table. So, so do you have any questions? Did everyone understand this? Okay, so I'm going to assume that everyone understood and you don't have any questions. If you have questions, you can ask me in the next class. So we'll have a quiz on Wednesday, and that will be from SQL. I'm not going to have design on the quiz at all. So it's going to be from SQL, and it'll be mainly about aggregate functions, because that's the stuff I haven't tested you yet on. So other than that, other than the quiz, we are going to be talking about design for a while now. So if you don't have any questions, I will see you on